the most famous of hotspots is probably Hawaii. What makes Hawaii so special and what makes all hotspots special is they do not occur at plate boundaries. So on the AP exam, if they give you a map and they say which letter represents hotspot volcanism, well, you would choose one of these three places, whatever letter they have decided to put on there. They usually put Hawaii. Okay, so the giveaway for a hotspot is that it is in the middle of a plate. Now notice it can be in the ocean or the continent, does not matter. Now there are a few more hotspots than these three, but these are the three well-known large hotspots. The other thing that's interesting about a hotspot, as opposed to a normal boundary, the boundaries can move and shift. We know this because of Pangea, right? Those continents have drifted all over the place. But a hotspot does not move. These guys kind of stay in place forever and ever and ever, at least as we've noticed so far. We have proof of that. Let me show that to you. They were all born in the same place and they slowly drift off as the plate slides. So the Big Island is growing right now, and it's the youngest when we look at the age of the rocks. But if you go to the northwest, you have Maui, which is a little bit older, 1 million years old. And that tells us that Maui used to be on the hotspot, and it has drifted over the last 1 million years to the northwest. So the hotspot stays in place, and the plate moves across it. And so that means that Kauai, way out here, that's 5 million years old, 5 million years ago, Kauai sat right here. And these other islands did not exist yet. So every single Hawaiian island was originally in this spot. When we look at the ocean floor of the Pacific, we see that it's not just the 7 or 8 Hawaiian islands that make up this record of the plate movement. But on the ocean floor, we see all the old islands. So we have 65 million years of history of where this Pacific plate has moved. And think about how we calculate speed. Miles per hour, right? Distance divided by time. So we know the distance, and if we know the age of the rocks, then we know time. And that's how we calculate how fast plates move. It's pretty simple, actually. So we know that the Pacific plate moves about 8 to 10 centimeters a year. And it's all because of the Hawaiian hotspot that helps us calculate that. Here's another famous hotspot. This is the one in North America that we call Yellowstone. Some of you have probably been to Yellowstone National. It's a very interesting park. It's got a lot of the same qualities as Iceland, where the magma is very close under the surface. So there's a lot of what we call hot groundwater features, things like geysers, hot springs. One of the big differences between Yellowstone and Iceland, in Iceland, you can get in most of the hot water features. In Yellowstone, they're boiling. But that magma underneath is in some places less than a mile beneath Yellowstone Park. Now, remember, the big western states are big, they're huge. And so to put this in scale, we've got Montana and Idaho. This is called a magma chamber. And the magma chamber, the hot spot underneath Yellowstone, we think is possibly the biggest one in the world. This thing is almost 3,000 degrees and it is gigantic. Now, we call this a super volcano. What this thing does when it erupts is it's a continental game changer. It causes drastic climate change, equivalent to when the asteroids hit and killed the dinosaurs. It blocks out the sun.
So you said it would blot out the sun?
Yeah,
so would it only do it over the United States, or would it do it over the entire world?
pretty much the whole northern hemisphere would get blocked out. We've seen smaller volcanoes do it already when humans have been around. There's one called Mount Tambora in the early 1800s, and it blocked out the sun in Europe, caused all the crops died. They call it the year without a summer. and there was massive famine and drought around the northern hemisphere.
So people in like Australia and Europe and Asia, they wouldn't really feel the effects.
It's hard to say because if we compare it to what the asteroid did, we call it the Cretaceous Tertiary boundary when the dinosaurs died. That was 65 million years ago. That hit mostly in North America, but it kind of killed things in the southern hemisphere too. So the Earth, we're going to get to this in ecosystems, but the Earth has hit the reset button a few times. We call them mass extinctions. And the worst one that we've seen that we know of based on fossil evidence, it killed almost 90% of living species on Earth. And I don't mean it killed 90% of what was alive. It made 90% of the things that existed go extinct, never to be seen again. And so brand new species came out of that. So when the dinosaurs died, that one killed about 60% of species. And it allowed for the emergence of the age we live in now, which is where mammals dominate the Earth. So the reason that mammals evolved so well was that they were able to burrow and live underground after that event. So that then eventually led to even humans. So your best bet for a big disaster, be it volcano, asteroid, or nuclear event, your best bet is to live in a cave. And we live in a great spot for that because there's lots of caves in southern Indiana, Kentucky, Tennessee. Well, here's some vocab for you. You can screenshot that. You can write it down. You can go back and pull up the video later on. That's all that is up to your choice here. I see some of you writing, so I'll pause and let you take care of that. On the news, they usually tell you the epicenter, the town that the earthquake was closest to. They hardly ever tell you the focus. The focus is the exact spot. You know, it may be 25 miles underground southwest of Los Angeles. They're just going to say near Los Angeles. It's called the elastic rebound theory. If I take a rubber band and I stretch it out, that's the elastic part, right? And I could stretch it so much that it breaks or tears. If I do that, it's going to snap back to its original shape. But I'm going to have two pieces instead of one. So that's what we mean by elastic rebound. Another example that they love to use is I could take a stick. I usually take a meter stick in class. Sometimes I break it. So you bend the stick, right? And the stick starts to curve and you know it's going to break. At some point, you're going to have just enough force, but it's going to surprise me. I don't know that exact minute that it's going to snap. And when it snaps, it can scare me, right? And that sudden release of energy, we know it's coming, but we don't know exactly when. That's elastic rebound. We're getting very good at predicting volcanoes, but we still have very little clue when an actual earthquake is going to happen. One of the biggest challenges is that earthquakes happen deep, the focus, they happen deep in the lithosphere. We can't get down there to relieve the energy or to examine it. So we just don't know how much it's locked up. So when we say California is going to get a big earthquake, it is like a 3-decade window that is really just an estimate. We've already talked quite a bit about this boundary. This is the San Andreas Fault, and it's the one that I think they'll ask you about. Remember, it is a transform boundary, which means sliding. So it's not converging or diverging. And I pulled up on USGS, which is a pretty good government site about all things geology. They can plot earthquakes on any given day, and they can plot you a week's worth, a month's worth. And so I pulled up a random one last year, 2 years ago. There were 217 earthquakes within the last week in California. Most of them are quite small, but what interests me here are the clusters. This is the San Andreas Fault. You see that line? I mean, the earthquakes show it, right? The earthquakes tell you where the faults are. And we don't worry about right up here by San Francisco. And we don't worry about down here right by Los Angeles. Where we worry is right here. where there are no earthquakes, because that means the stress is building up. And that's where it's going to snap, and it's going to affect San Francisco and Los Angeles on both sides. So it's the dead spots that are of concern to us. Just like hotspot volcanoes, there are hotspot faults. We don't call them that. We just call them mid-plate faults. But one that most people are not totally familiar with is called the New Madrid, and it's in Missouri, and it is an old riverbed fault. So the river changes paths and it leaves behind where it had eroded. And when the ground shifts in the Midwest, there is potential for very large earthquakes. Most people know that the West Coast has earthquakes because it's the plate boundary. But a lot of people do not realize what we call the risk for a big earthquake in the Midwest. Now, are we prepared? In California, they go back and retrofit buildings. They design codes that allow buildings to withstand large quakes. Do we do that in Indianapolis? Is our downtown built for a big earthquake? No, not one bit. And when this earthquake went off in 1812, and there was one in 1811 as well, these are two of the three largest earthquakes the United States has had in modern times. Did we have a big downtown in 1811 with tall buildings? No, we weren't even a state yet. Did we have St. Louis and Louisville and Memphis and New Orleans and Chicago? And we didn't have all these cities. There's a big difference here. You look at the big quake in California, 6.7, and in 1895 they had a magnitude 6. Look how much further the waves go in the Midwest. It has to do with our bedrock. We have a different bedrock than they do out west, and it is the density of the bedrock. Waves travel easier through the Midwest bedrock, and so the waves go much further. When this quake happened in 1811, it rang church bells in Boston. It caused the Mississippi River to flow backward for a while. Next week, we're starting dirt. Yay. Is there anything more exciting than dirt?